The RC time constant, also called tau, is the time constant of an RC circuit, is equal to the product of the circuit resistance and the circuit capacitance, that is. It is the time required to charge the capacitor, through the resistor, by a per mil 63.2% of the difference between the initial value and final value, or discharge the capacitor to a per mil 36.8%. This value is derived from the mathematical constant E, more specifically as voltage to charge the capacitor versus time, charging, discharging. Cutoff frequency. The time constant is related to the cutoff frequency Fc, an alternative parameter of the RC circuit, by or, equivalently. Where resistance in ohms and capacitance in farads yields the time constant in seconds or the frequency in hertz. Short conditional equations, Fc in hertz equals 159,155/I in a microsecond, I in a microsecond equals 159,155/Fc in hertz. Other useful equations are, rise time, standard time constants and cutoff frequency S for pre-emphasis de-emphasis RC filters. In more complicated circuits consisting of more than one resistor and or capacitor, the open circuit time constant method provides a way of approximating the cutoff frequency by computing a sum of several RC time constants. Delay. The signal delay of a wire or other circuit, measured as group delay or phase delay or the effective propagation delay of a digital transition, may be dominated by resistive capacitive effects, depending on the distance and other parameters, or may alternatively be dominated by inductive, wave, and speed of light effects in other realms. Resistive capacitive delay, or RC delay, hinders the further increasing of speed in microelectronic integrated circuits. When the feature size becomes smaller and smaller to increase the clock speed, the RC delay plays an increasingly important role. This delay can be reduced by replacing the aluminum conducting wire by copper, thus reducing the resistance. It can also be reduced by changing the interlead dielectric to low dielectric constant materials, thus reducing the capacitance. The typical digital propagation delay of a resistive wire is about half of a times C. Since both L and C are proportional to wire length, the delay scales as the square of wire length. Charge spreads by diffusion in such a wire, as explained by Lord Kelvin in the mid-19th century. Until Heaviside discovered that Maxwell's equations imply wave propagation when sufficient inductance is in the circuit, this square diffusion relationship was thought to provide a fundamental limit to the improvement of long-distance telegraph cables. That old analysis was superseded in the telegraph domain, but remains relevant for long on-chip interconnects. See also, cutoff frequency and frequency response, emphasis, parenthesis, de-emphasis, exponential decay, filter and transfer function, high-pass filter, low-pass filter, band-pass filter, RL circuit, and RLC circuit. References, http Hyperphysics Phi AST Argsu Eduelectric Captis HTML, Andrew Gray. Lord Kelvin. Denter, Ido Yavits. From Obscurity to Enigma. Berger Currency User. ISBN A3-7643-5180-2. Jarinomi, Hanu Tenanen, Jouni Isu, and Axel Janch. Interconnect-centric design for advanced SoC and No-C. Springer. ISBN A1-4020-7835-8. Scott Hamilton. An Analog Electronics Companion. Cambridge University Press. ISBN A0-521-68780-2. External links, RC time constant calculator, conversion time constant to cutoff frequency Fc and back, RC time constant.